Hello, my name is Rachel Domagulski, and I am a PhD student at Michigan State University. I'm super excited to still get to speak with you all today. I'm really glad that the organizers were able to make this conference remote. Thank you so much for letting me speak. And today I'm going to be talking about inferring relationships through graph theory and social network analysis. So what we're going to be focusing on today is how do we find the backbone of a bipartite projection? So we're going to get to what all of those words mean, but our main goals here are if we find some social relationship that we want to study, and then we represent it as a graph or a social network, how do we figure out which edges of that graph indicate strong relationships, and specifically strong positive relationships or strong negative relationships? And this is all joint work with Dr. Bruce Sagan, who is one of our keynote speakers for this conference, and Dr. Zachary Neal, both from Michigan State as well. So to start, just a little background. What is a graph? Well, a graph is just a set of objects called vertices and two element subsets of those vertices called edges. And we can represent a graph visually, like we see in the top right here. This graph has four vertices, A, B, C, and D, and there are four edges between those vertices. For instance, there's an edge between A and B, and in this case, it has a weight of 2. So graphs can have weights or be unweighted, which we would represent as just plain edges between them with no numbers. So we can represent a graph like this in a visual format, or we can represent it as an adjacency matrix. Now, an adjacency matrix is an n by n matrix where n is the number of vertices we have, and each entry of the matrix represents the weight of the edge. So if it's unweighted, we just say the entry is 1 if there's an edge between that corresponding row and column. And if it is weighted, we place that weight in that entry. So if we look at this matrix down in the bottom right, and we look at the first row, so A, and the C column, we see the number 3. That represents that the weight of the edge between A and C is 3. So social networks are just taking this graph theory object and applying it to social relationships. So if we find something we want to study, such as, say, friendship, maybe between students in a classroom, we represent them as our nodes or our vertices, and then we put an edge between two individuals if they're friends. And we could add a weight to this to represent the strength of that relationship. So a super strong friendship might get a 3, and a decent friendship might get a 2. And then if people are not friends, we would have just no edge between them. So I want to make a case before we get into bipartite graphs for why we're going to need them. So knowing social structure is very important. So this can help us understand flow of information. Say we're looking at the social network of a company. We could figure out which groups of people work really well together. We could see who controls the resources of a supply chain. And ultimately, the more we know, the more we can have better working, happier groups of people. So it's helpful to know both positive and negative interactions so that we can achieve this goal. So let's say we find a group of people that we want to study, and we want to figure out how do we represent them as a social network? How do we put them in a graph where we can represent the relationships through their edges? So we could ask them, we could take a survey. We might say, who do you work really well with? Who have you worked with in the past? But if we also want to know negative relationships, we end up with a problem because it's going to be pretty awkward if we just say, who do you not like in this group? So we need to find a better way. So signed networks, which are those with both positive and negative ties, inherently difficult to capture because we have standard network issues anyway, where if we have a large group of people and you want to collect data on them, you might have survey fatigue, people might forget a couple names to mention, it could be very costly. And then if you want to ask about negative relationships, there could be repercussions. Someone could be lying. It might cause emotional distress, or you might just simply not be allowed to ask. So if we find a social structure that we want to study, that we want to represent with a graph so that we can analyze its properties, how are we supposed to do that if we run into these issues? So one way we can do this is to infer them through what we call bipartite networks, which is a bipartite graph. So a bipartite graph is a graph that has two sets of vertices. We can call them U and W. And each edge is of the form ij, where I is a member of U and J is a member of V. So what that means is we have two sets of things, and edges can only go between sets. They cannot go within sets. So in this graph to the right, you'll notice that there are no edges between the vertices that are letters, and no edges between the vertices that are numbers. Similarly, we can also represent these with an adjacency matrix, but we call this now a bi-adjacency matrix. The rows here will represent elements from our first set, vertices from our first set, and the columns will represent vertices from our second set. And then we place the weight of the edge in the corresponding row and column. So A has an edge to 1, so there is a 1 in the A1 entry. So if we want to make this a network instead of a graph, all we're doing is thinking of these as two different sets of things, usually where the first set is something like people, something that has agency, and the second set could be something like an event, or we also call this an artifact. So instead of asking for person-to-person relationships, we're now just looking at who participated in this event. And this is often much easier to capture because we don't actually need to survey all these people about their interpersonal relationships. We just need sort of their participation data. And what we want to notice here too is that if we look at the row sums of these matrices, of the matrix, and the column sums of the matrix, the row sums, they're going to just tell you how many events each person participated in. And the column sums are going to tell you how many people participated in each event. So this is going to come back later. All right, great. So we have this bipartite network. We have a bipartite adjacency matrix. We know that it represents something about our social situation. How do we transform this into a graph where we can see relationships between the people? Well, the way that we're going to do this is through a bipartite projection. And what that is we take the bipartite matrix, which we call B, and we multiply it by its transpose. So that's what this is indicating here. We have people via events, our bipartite adjacency matrix. We multiply it by its transpose here. And we end up with an adjacency matrix of a weighted graph. So here, each cell, I and J, is going to represent how many events vertex I and J have co-attended. So for instance, if we look over in our first matrix here on the left, person A and person C, they both went to event 1, and they both went to event 4 and event 5. So the PA-PC entry here is 3, because they went to 3 events together. But if we look at B and D, they never were at the same event. So they have a 0 in their corresponding entry. So bipartite projections are weighted graphs. Each edge in our graph represents the number of events that two people have attended together, so co-attendance. So here between A and C, if we went back and looked at our bipartite adjacency matrix, we'd see they were both at the same 3 events. So now we can ask a couple questions. So if person A goes to every single event, should that tell us something about their relationship with person B? And what if D never attends an event with person B? Could we say they're avoiding each other, or did that sort of happen at random? So how many events should we say that two people have to attend together before we can consider them friends? And how few events do they need to attend together before maybe we say that they're enemies or avoiding each other? So our goal is to take this weighted graph, which can be difficult to analyze and very difficult to visualize if there's a lot of vertices. And we want to reduce it to only the most important positive and negative relationships. And we're going to call this our backbone network. The backbone network should represent the actual relationships that are going on. So we've inferred this weighted graph using basically like third-party data, and we want to reduce it to know the actual network that's happening behind the scenes. And the backbone matrix is going to end up looking something like this. So instead of having this weighted adjacency matrix, we want to end up with a signed adjacency matrix, where a 1 will indicate a strong positive relationship, a -1 would indicate a strong negative relationship, and a 0 would mean we can't infer that there's a relationship between those two people. So what value should we pick to make this determination? Should we say if everyone went to at least one event together, we could say there's a positive relationship there and they're friends? Should it be 5? Should it be 100? In general, for large graphs, this is going to give us something that looks like this, just a hairball, tons of edges between everyone. And we're also going to lose a lot of information. We're not going to keep track of those people that attended more events than others and events that were attended by more people than others. Maybe there was an event that was required for everyone to go to. That shouldn't give us any information about friendships because everybody was required to be there. And maybe there's two people that never go to events together, but they're always at, say, 2 events together. That might be more indicative of a relationship than having a high number of co-attendants. So we want to be a little more careful. We want to actually pick threshold values where we can say if you hit this amount, we can say there's a relationship. Those thresholds we want to be conditioned on each person. We want to look at how many events did each person individually attend, and of those events, were they attended by a ton of people? Were they only attended by a few people? And this is going to give us a couple different ways that we can choose individual threshold values for our backbone. So specifically what we're looking for is to figure out what this backbone subgraph is. It's a subgraph of our original graph G. It contains only the most important edges. And we're going to pick a threshold, Tij, for each pair ij in our network. So that means for each pair of people, they're going to get their own threshold value. And if we pick an upper and a lower threshold, then if the observed weight we see is greater than the upper threshold, we might say there's a positive relationship. If it's lower than that lower threshold value, it's a negative relationship, and 0 if it's in the middle. And now this is important because we actually have a different value for different pairs of people. So we talked about we might want to keep track of how many events each person attended, how many people attended each event. We can think of these as sets of restrictions. So if we have our bipartite graph B, we project it and find our projected graph G and look at each of the edges. We want to compare those edge weights, Gij, to probability distributions that describe the graph Gij star, which is created from the projection of a random bipartite graph under a set of restrictions. So maybe we look at all random bipartite where we've fixed the row and column sums to be equal to that of the row and column sums in our original graph. Or maybe we only fix the row sums to be equal to our original graph B, but we let the column sums vary. Or maybe we let them both vary. When we do this and we look at all those possible bipartite graphs in our set of restrictions, what we end up getting is sort of a distribution that looks like this. Let's say we're looking at the edge weight between person I and person J, and under the distribution, on average, it's about 4. But in our actual data, we said, well, person I and person J, they actually had a co-attendance of 8 or 9. And our probability distribution says that that's very unlikely. Then maybe we assume that's a positive relationship. They are attending more events together than we would expect them to under this random set of circumstances. And we can look at the opposite. If they're only co-attending very few events, but when we looked at the projections of all these random bipartite matrices, and we said that they should be attending about 4 events, maybe we assume that's a negative relationship. So I want to dive into a couple of the different probability distributions we can use to describe some of these circumstances, and specifically show you how it looks when we visualize real data. So this is sort of a snippet of some real data I've been working with. These values are not exact, but in reality, I'm working with a very large data set of senators and bills they've sponsored. So this is an example of what this data looks like. It would have all of the senators in a certain session, all of the bills that were proposed, and then each senator gets a 1 if they sponsored or co-sponsored that bill, and a 0 if they did not. When we take this as our bipartite graph and project it, we get a value, say Senator A and Senator C. If they had a value 3, that means they each sponsored 3 of the same bills. So they co-sponsored 3 bills. And we can sort of assume that this would be indicative of a relationship based on you might be working more with people who share your political ideation, and maybe you're choosing not to work with people who are of separate parties. And it yields very interesting results. We sort of expect there to be more positive relationships within party and more negative relationships between parties, simply because of the political polarization in America. So when we do a backbone here, if we use a backbone method, we apply some threshold, we're going to see positive edges if 2 legislators have sponsored the same bills more often than we would expect at random, when we either fix the number of bills that they sponsored, or it's roughly fixed, and fix the number of people that sponsored each bill, or it's roughly fixed. And same thing with negative. They'll have a negative edge between 2 senators if they've sponsored the same bills less often than we would expect under one of these random set of circumstances. So I'm going to show you 3 different backbone methods, and we're going to look at the plots that they create when we graph them, and we can see if the backbone methods are actually giving us something more informative than if we just chose a single threshold. So first, let's take a look at what happens if we just chose every pair of senators that sponsor at least 1 bill together gets a positive edge. That looks like this. So this is sort of inherently the problem I was mentioning with the hairball graphs. So we just sort of have this blob. It's uninformative. It doesn't tell us very much. We can't really see if there's any sort of social structure going on here. In this graph, our red vertices are Republicans, blue vertices are Democrats, and an edge represents a positive relationship. And this is just if they sponsored 1 bill together, there's so many bills that it's so likely that they're going to sponsor a bill together that we don't get any sort of extra information. So let's try to do a little better. Let's say instead of just choosing that value of 1 for every single edge, what if we condition it based on the row sums and the column sums? So let's fix the row sums and let those column sums vary. So in our example, this means each senator is going to sponsor the exact same number of bills, but each bill, it could be sponsored by a different number of senators. So this is actually going to be modeled by the hypergeometric distribution. So this models the probability of having small k successes in a random sample of size little n from a population of size big N, where the total of big K objects are classified as success. And it's given by this probability mass function. And we can see that our scenario is actually modeled by this distribution if we pick these things for our variables. So for each edge in our projected graph, so that's Gij, if we let n, the population, be the number of events possible, so the number of bills in our case, we let little n be the number of events that J participated in, or the number of bills that Senator J co-sponsored. If we let k, the number of objects that could be a success, be the number of events I participated in, then what we're actually looking at is little k, the number of events they had in common, the probability that they actually co-sponsored the amount of events. Sorry, the probability that the two senators actually co-sponsored the number of bills that we saw in our actual data. So this will represent the scenario that's going on when we fix the row sums and we let the column sums vary. And when we graph it, we end up with something like this. So we can see that we're starting to have a lot of edges that are within party. There's still a lot going on between party here as well. There's a lot of purple, but there's a little more structure that we can see. So let's see if we can do a little bit better. What if now we allow both the row and column sums to vary a little bit? So we're not going to fix either of them. So this means each senator is going to sponsor roughly the same amount of bills, and each bill is going to be sponsored by roughly the same amount of people. So the catch here is that we want the expected row and column degrees to be equal to our original bipartite matrix, or bipartite graph. We found that this is actually modeled by the Poisson binomial distribution. So I thought I'd show you how we can see that our scenario is modeled by this. So the Poisson binomial distribution is the distribution of a sum of independent Bernoulli trials, where each of these might have their own specific probability of success. And a Bernoulli trial is just like a coin flip. So it's a random experiment with two outcomes. That might be success, failure, heads, tails, yes, no, etc. So specifically, if we have n of those Bernoulli random variables, let's call them x1 through xn, and they each have their own probability, where the probability of xi equaling 1 or equaling success is pi. Then if we look at their sum, the sum has Poisson binomial distribution with the parameters p1 through pn, where those are those probabilities. In our case, we can find these p1 through pn's by first looking at the bipartite adjacency matrix. So we want to first assign a probability for the entry Bij to be 1. So that means the probability of person to event, person participating to event. What's the probability? That's going to be 1, meaning the edge exists, versus 0, the edge does not exist. And we find those probabilities using a binary regression model that we base on the row and column sum variables. So you can use like a logit link, a probit link, log, etc. Something that's going to give you a probability of these being 1. And then we look at what the value in the projection is. So when we do that matrix multiplication of the bipartite graph by its transpose, we're actually just multiplying all these sort of Bij numbers together, right? So the entry Gij is just going to be equal to this sum here. And if we look at the probability of this GIJ, whenever we're looking at the probability of two entries in our bipartite adjacency matrix multiplied together, since these are independent occurrences of these edges, we can separate their probabilities to be multiplied together, and we get that the overall probability is just P sub ik times P sub jk. Now we can do that for each of these n multiples, and we can see that the entry Gij is Poisson binomial with the parameters P1 equal to that first multiplication and Pn equal to the nth multiplication. So what does this do to our graph? Actually a lot. So same Senate co-sponsorships. If you remember in the hypergeometric, we had a lot more purple lines going on here. Now we have most of these positive edges are located within party, and there's only a very few going between party. So we are sort of reducing the density of our graph so that we can see only the most important edges here. And this is, again, to be expected. We know that the US political system is polarized, so we expect most edges to be within party. So I have one last model to show you, and that's called the fixed degree sequence model. And guess what? It's going to fix the degrees. So it fixes the row and column sums of our bipartite matrix. So for the past two, we used hypergeometric distribution and Poisson binomial distribution. We don't have a probability distribution to describe this null model. So instead, we approximate it. So we create an empirical distribution. And we do that by constructing a bunch of different bipartite graphs. So we want to basically randomly sample the space of bipartite projections. So we start by creating random bipartite graphs with the same row and column sums. And to do this, we're using the curveball algorithm. And then we project those to obtain our random weighted bipartite projection G star. Repeat this some number of times, 1,000, 10,000, so that you can accurately sample the space. And then we check how often was our observed value above the values that we got in our random projections. So again, think back to the example where we had sort of the normal looking distribution. We want to see, is our value falling above what we get in all these random trials or below it? And again, if we run this on that same Senate data, we end up with this graph here. So again, most edges are within party. There's very few edges between party. And this is, again, modeling the positive relationships here. So we can see that people are most likely collaborating with people that share the same views as them in the Senate for this data set. So backbone extraction, it's super powerful. It lets us take weighted graphs, which are inherently very difficult to analyze and visualize, and sort of pick out the most important parts. Just using bipartite projections lets us infer networks we might not be able to capture by conventional methods. You can't always create large enough surveys. People might lie. We might need something where we can look at third-party data to see what's going on between individuals. And then when we're picking a specific threshold value for each pair, for each edge, and picking one that's conditioned on the row and column sums, we start to see some more inherent sort of like what's actually going on in the network. So our goal is really just to pick a model that really will give us that will really represent what's going on in the actual network. So we're going to continue to develop new methods of backbone extraction and find probability distributions that describe different sets of restrictions. If you would like to try this for your own data set, see if it could help you in your own research, all of the methods that I've talked about are available in an R package that we've put together. You can install it from CRAN using install.packages backbone. or you can visit our CRAN page. Or I also have latest developments on my GitHub page, which is domagal9/backbone. And I'd love to hear if you try it out. Tell me what works, tell me what didn't work, tell me if you found something really cool based on your own bipartite data. So anything that's people participating in events, throw it in there, see what you get. Thank you so much for listening. These are some of my references here. If you have any questions, I'd love to chat during the Q&A on Saturday. And thank you again. Bye.